Before we can understand exactly what's involved in providing internet connectivity, we need to understand a little bit more about the actual model that we're talking about. So when we look at this, the main thing that we want to realize is that we need to work with the TCP/IP internet layer in our reference model. Now, the internet protocol is going to be the tool of choice for communicating to the outside world. Now, we've discussed the link layer. The internet layer is where we have our layer 3 traffic. That means we're going to be working with packets. Now, the moment we start working with packets, we understand that we're using logical addresses. Now, logical addresses are significant for us. And logical addresses are going to be the way we actually communicate with the outside world when it comes to sending information to the internet and receiving information that we solicit back from the internet. Now, when we look at how this goes into place, we need to understand that there's a number of characteristics associated with our IP protocol traffic. Of these, we have quite a few listed here on the presentation. Let's look at those. First of all, the IP traffic is going to operate at the internet layer of the TCP/IP stack. So again, right here, just to illustrate that point. The other thing here is that we need to recognize that IP protocol is connectionless. In other words, it's not going to maintain state information. So there's not going to be a process whereby I know that I'm actually successfully communicating with the distant end. There's no correction mechanism if I lose connectivity. I'm just simply going to lose the information that I'm working with. Now, also we need to recognize here is that packets are the PDUs that exist at the internet layer in the TCP/IP model, and it's going to be the packets that we're going to be working with, and we're going to treat those packets just like it says here. We're going to treat them independently. Now, what we are going to do is we're going to look at sources and destination based on this concept of addressing. Now, it's really important, but it's also kind of problematic to a CCNA student because the addressing that we're working with, layer 3 addressing, packet source and destination addressing, is hierarchical by nature. Well, I got it written down here. So it's actually hierarchical addressing. So what we're going to find here is there's an order of operations. There's going to be role-based assignments based on a particular address. For instance, we're going to find out that we're going to have an address that's going to represent the network. We're going to have an address that can represent an individual host on a network. We're going to have an address that's going to actually represent a broadcast range that's specific to a network segment that's referred to as a directed broadcast. So looking at this, all of these have different meanings and all of them have different values. The main idea here is that across the internet, everything's going to be best effort. There's no guarantee. There's no asserted or assured quality of service that exists on the internet. And like I said, there's no session mechanisms in place that are going to allow us to recover from the idea of losing data. So there's no data recovery features whatsoever. And it's going to be operational whether or not we're using fiber or whether or not we're using copper. It's irrelevant. Media doesn't really matter because all that happens is we use whatever media we have to transport the IP packets that we're using to exchange between source and destination. The last thing here is that we're going to realize, or we need to understand, that our IP protocol comes to us in two flavors. We have version 4 and we have version 6. IP version 6 is making a huge burgeoning effort into the majority of networks. In fact, I know half a dozen engineers who are traveling all across the United States right now implementing version 6 conversions from version 4. So again, it's going to be something we definitely want to understand, and it's so important that Cisco has actually taken the last module of this class and devoted it purely to IP version 6. The majority of the stuff that we're going to be talking about from this point up to there, though, is going to be IPv4. Slightly outmoded, but still used in over 90% of the networks that are currently existing in the world today. Now, when we look at exactly what's going on, we need to understand how these addresses are represented. Now, I mentioned previously that they're going to be 32 bits in size. So as you can see above my head, we have an address range. Now, what we're going to need to understand here is it's going to be 32 bits in size, and it's going to be broken up into 4 octets. An octet is a group of 8 binary values. Now, when we look at how this is implemented, what we're going to realize is that this drawing seems to indicate that it's half, but it's not. Of our 32 bits, some value of them are going to equal what's referred to as the network. The other value, so it's going to be Y is going to represent hosts. Now this line right here looks like it's representing 16 and 16, which is a capability, but it's not necessarily set in stone. It could be that we're using the first 24 out of the 32 for the network, and then the remainder would be used for hosts. But the main thing that we need to recognize here is that it's broken up into the idea of the network and the host, and those are going to be the two parts that we use to illustrate what's happening. The network ID is going to be what we use to identify the network that hosts are going to be a part of. Now, I use the corollary for where I live. I live on Tinsley Avenue, or Tinsley Drive. Sometimes I forget where I live. Now, if Tinsley Drive is the street, then I need to have a street address. So that address for me may be 2 Tinsley Drive. And we may have 10 people living on my street. Well, when we look at this, the correlation between these values is the network corresponds to the street, the host value corresponds to the house number. So in other words, a host is going to be a destination on a network segment. So when we look at this, what we're going to find is this information, this part right here, the network is going to be used by routers to actually maintain information about destinations. So if I want to get to Tinsley Drive, I'm going to be able to look in a routing table or a map, and I'm going to know which direction to go in order to be able to get there. That's really and truly all there is to it. Now the host values identify specific or individual hosts on that network segment, and it's going to be assigned to organizations, and each of these addresses are going to be assigned to individual devices in those organizations. So if I have 10 computers, I can have my network value, and I can have computer 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I have 200 computers, I can have 1, 2, 3, 4, 99, 100, all the way up to 200. So when I keep in mind that the more information I have for my network, the less information I have for my hosts. And we're also going to understand or have to recognize the fact that there's authorities, like the numbers authority, that is going to issue addresses that are going to be assigned as networks. And as CCNAs, we're going to have to know how to manipulate those to have them represent the idea of a subnetwork. Now, I don't want to lose you guys. Every time I've ever taught CCNA in a brick and mortar environment, the moment I start talking about subnetting is normally around lunch on like the second day. And what ends up happening is that during lunch, over half of my students don't come back because they're just absolutely terrified of the concept of creating sub-networks. Now, the way we're going to describe it is I'm hoping that I'm going to simplify it with regard to exactly what's involved and how it operates. But I can't stress enough how important the idea of subnetting and variable length subnet masks are in the confines of preparing for any Cisco certification exam, whether it's CCNA, CCNP, or even CCIE. Now I'm going to show you some shortcuts that I've used. I don't even really like to call them shortcuts as much as I'm going to call them the idea of using a reference. But when we go in and we start looking at how we're going to do subnetting, we have to understand what it is we're doing, and there's no better way to understand what is involved inside of an IP packet there's no better way than looking at the headers. And that's what we have here. We have the IPv4 header fields. Now notice, there's more here. This is substantially larger than a frame. In fact, if we were to look at this, bear in mind, this is a layer 3. This is the networking layer of the OSI model, or the intranetwork layer of the 4-layer model. Now, that means that it's going to go down to layer 2, which is the link layer, or the media access layer, that's going to go out across the wire. Now, the information that goes across the wire is going to be much smaller than this, because what we're going to do is we're going to break this up into our payloads and send it down this link. But the main thing that we want to understand right now is that what goes into this particular header. Notice I've got some values that I didn't have before. Notice I have a time to live. The idea with a frame is a frame has no TTL, no time to live. Now that's good. That's possibly a bad thing, because what ends up happening, let's say I have a switch, SW1, I have SW2, SW3, and SW4. And these switches are connected in a loop. And I want to send information. Let's say I have a host, and I want to talk to this host down here. Well, the possibility exists where if I don't remember, I send my request over, I'm saying I'm going to source A, I'm from source A, and I want to communicate to this host here, so C. Well, if this device doesn't know the identity, it's going to flood that information out. Well, if this device doesn't know that entity, it's going to flood that out. It's not going to flood it out on the ports that it came in on. But what ends up happening here is that when this message arrives here, it arrived on this port, so I'm not going to forward it out, but that's not going to stop me from sending it out this port. This one arrived on this port, and it's not going to stop me from sending it out on this port. So what we see here is that I get the capacity to get these bidirectional loops that can form in my infrastructure where these packets can bounce around forever. Well, this is a problem when it comes to a frame, but when it comes to our idea of an IPv4 packet, we have this value of time to live, which means every time I go from a hop, I'm going to decrement my time to live. The moment I get down to 0, my packet is going to die. Now, notice also I have my source address, this is my IP address, and my destination address, which is also an IP address. And I have options, and I have the capability of forming padding. So when we look at this, what ends up happening is this packet, by virtue of the fact that it's larger, all of this header information means I can carry more information. Now the problem is that of the information that I carry, more of it is now header. Now keep in mind, switches use the frame headers, which were much, much smaller, so I can actually send information where each frame is going to carry more information than header. And it is quite possible, even when we move into areas like voice, where we can have information that we're exchanging that's 80% header and only a small payload. So again, these are things that we want to keep in mind that can impact how we exchange information between our devices. And it really just boils down to how we're going to represent the information. And we have to understand that there's two modes of representation. There's binary and there's decimal. Decimal is human readable. We can look at it and have no problem. The number of 10 equals the number 10. In binary, 10 equals 2. 1 0 means 2. And a lot of people just can't get that grasped. And that's one of the things that really, really causes problems when it comes to concepts like subnetting and variable subnet masking. So let's look at this table. This table gives me a binary equivalent to a decimal value. So here, notice 0 is 0 in binary, 1 is 1, but notice 2 looks like 10. In binary, what we have to recognize is that we have different numbering systems. So let's say decimal is here, and we have binary here. In decimal, I can have individual digits that range between 0 and 9 in their value. In binary, I have 0 to 1. Now, if I want to start counting, imagine, I used to do this when I was a kid. Imagine you're watching your dad's odometer in his car. Now, what we find is that as this number right here, and I'll change pen colors just to emphasize it, as this digit, or as this space in the odometer, as we travel further, this number changes. 3, then goes to 4, then it goes to 5, then 6. Well, when it gets to 9, what's the next number on the wheel? Remember, it's only 0 to 9. So what ends up happening is as that odometer rolls, what we're going to find is it's going to go to 0 and start this cycle all over again, and it's going to cause this one to increment. So that's going to be 1 mile, 2 miles, 3 miles, 4 miles, 5 miles, 6, 7, 8, 9. Then it's going to go to 0 again, and it's going to increment this one to 1. So it's going to be 11, 12, 13, 14. And it's going to go through this process until ultimately it goes out to all of its values. Well, in our IP addressing, my range is going to be 0 to 255. So I have 256 possibilities in each of my octets, and as I described, I have 4 octets. So I've got 8 values, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Then I have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So I have 4 groups of 8 binary values. So each one of these can add up to 0 to 255. Now, when we start looking at binary, we have to understand when we were looking at what happened in our decimals place, we had this. If I were to draw a number line, my number line would start with the ones place, the tens place, the hundreds place, the thousands place. So when I look at a number that says 1000, I know that's 1000, where if I look at 1011, I know it's 1011 in decimal. In binary, I have a number line, but what I've got is I've got the ones place, I have the twos place, I have the fours place, the eights place, the eights place, the 16th place, the 32's place, the 64's place, all the way out to what would end up being the 128's place. So that's the numbers that I can recognize and I can work with. So for me to look at this, this is readable, but if I look at it this way in binary, so if I go 0, 0, 0, all the way out to 128, all these zeros don't add up to anything. So if I start adding this up, that's going to be 8 plus 2 plus 1, so it's 8, 9, 10, 11, so that's 11. So the value 1011 is going to be right here, and notice it equals the decimal value of 11. I mean, it's that easy to add it up. People make it a lot more complicated than it really has to be. Now, what we're going to find is there's going to be a number of addresses that we're going to need to memorize, and those addresses are going to have values for us. But when we start looking at this process of conversion, we don't want to overcomplicate it. So like I said, we have a number line, and that's what I have drawn up here. And I recommend to every student, in fact, let me do that. I recommend that the moment a student walks into the CCNA lab, or the CCNA, I got lab on the brain. As soon as you walk into the CCNA testing center, they're going to give you some time. They're going to say, sit down, they're going to give you a laminated piece of cardboard, maybe two. You're going to get a marker, a dry erase marker. It's a pain in the butt to use. But the moment you walk in, before you start taking your test, you have the capability or the option, and I'm going to change my pen width here. You have the option to take a tutorial. Now that tutorial can take up to 15 to 20 minutes. Sometimes less, but normally it can take up to that range. Now the thing that you need to understand is until you finish that tutorial, your CCNA lab exam or your CCNA exam has not started yet. All right? So what I recommend to every student is go into the testing center and draw that number line. So we've got 1, 2, 4, 8, 16, 32, 64, 128. Now what I'm going to recommend students do is they add these up. So here's our number line. And it's very easy to memorize these. But the main goal here is 128 is 128. But what happens when I add 128 to 64? I get 192. When I add 192 to 32, I get 224. When I come here and add 6, 7, 8, 9, 10, and come through, I should end up with 240, 248, 252, 254, 255. Draw this number line out when you go into the testing center. Start your tutorial. During the tutorial, you can write stuff onto that pad, and this number line is going to save us quite a bit of time when it comes to doing math. It's going to help us with something called our slash notation, so like a /25, something also referred to as CIDR, classless interdomain routing, CIDR. We'll talk about that shortly. But the main thing here is this number line is going to save you some time. It's going to allow you to do math much, much quicker, because when it does come down to subnetting, you need to be able to do your subnetting in less than a minute. I mean, that's basically what's going to end up happening. That's what I highly recommend to all students. But sit down and draw this number line out. Now, what I'm going to do is I'm going to cut us back over to the presentation, and what we're going to see is the number line already drawn out for us. As soon as I can bring it back up. And there we go. So now, we see the number line. And where is that number line? Well, that number line is right here. That's our places value. So when I come through here and I say, I've got a number of 35. If I want to find out, or to convert this in, so I'm going to convert decimal to binary. So here's how I do it. Let me grab a pen. I'm going to do it in red, and I'll just do it right here. So I have 35. So does 128, is it divisible, or can I subtract 128 from 35? No, I can't. So it's going to be 0. Can I subtract 64? No, it's 0. Can I subtract 32? Yes. So once I subtract 32 from that value, what do I have? So I have 35 minus 32. That's going to be 3. So can I subtract 16 from that value? No. Can I subtract 8 from that value? No. Can I subtract 4 from that value? No. Can I subtract 2 from that value? Yes. 3 minus 2 leaves me 1. Can I subtract 1 from that value? Yes. So this number right here, this is the graphical representation of 35. So it should be 0, 0, 1, 0, 0, 0, 1, 1. So it's 0, 0, 1, 3 zeros, 1, 1. So that's going to be 35. Let's do another one. Let's just pick one that's not on the chart. Let's say that I want to do 127. So can I subtract 128 from 127? No. Can I subtract 64 from 127? Yes. So subtract 64. 3, 12, that leaves me 63. All right, so can I subtract 32 from 63? Yes. So 63, take away 32, that's going to leave me 31. Can I subtract 16 from 31? Yes. 16 from 31 is going to leave me 15. Can I subtract 8 from 15? Yes. 8 from 15 leaves me 7. Can I subtract 4 from 7? Yes. That's going to leave me 3. Can I subtract 2 from 3? Yes, it's going to leave me 1. Can I subtract 1 from 1? Yes. Now, doing this mathematical process, you're going to find that if you do it properly, you will have no remainder. And that's how easy it is. All you need to do is bring up that number line and do the math. So if we come up here to this value, I'm using the top part of the number line. I'll get into the significance of the bottom part very shortly. But again, that's going to be the whole value. So if I were to write the number line out like this, 128, 64, 32, 16, 8, 4, 2, and 1. Now, I wanted to take a value and see if I can formulate it. So let's do 256. So if I take 256, can I subtract 128 from it? Yes. What do I get left when I subtract 128 from 256? 128. Can I subtract 64 from 128? Yes. What do I get? When I subtract 64 from 128, I get 64. Can I subtract 32 from that? Yes. What do I get? 32. Can I subtract 16 from that? Yes. What do I get? I get 16. Can I subtract 8 from that? Yes. What do I get? I get 8. Can I subtract 4 from that? Yes. Actually, should have done this at 55. So 255 would have been 127, would have been 63, would have been 31, would have been 15, would have been 7, would have been 3, subtract 1, 2, yes. That leaves me with 1. Can I subtract 1 from 1? Yes. So the main value here is that 255 would equal binary 1.1111111. So it would have been 8 ones. Now that stands to reason because the value the highest value that I can represent is going to be 0 to 255 per octet. So again, this number line, the top part of this number line, can save you a lot of time in your mathematics with regard to breaking everything down. And again, I'll get to the bottom part of the number line shortly. But looking at how that all comes together, it really and truly just makes things much simpler with regard to resolving these mathematical equations. So draw that number line out. Take the time while you're doing your demo or your tutorial and draw the number line. Now the other thing that we need to recognize is the fact that our IP addressing, like I said, are hierarchical by nature. They're hierarchical because we have a portion devoted to network and we have a portion devoted to host. But we also have to recognize that we have ranges of addresses that are going to be broke up into different categories. The ones that I need you to know for the CCNA are Class A, Class B, and Class C addresses. And it's super simple if you understand the formula. And it's also super simple to memorize them. But if you lose it, if you forget something in the lab, sometimes we get into that in the lab, I keep saying that, if we get in the exam, if you forget something, it's always important that you know how to extrapolate it when and where possible. And what I want to do is I want to look at that, because what we're going to realize is that a Class A address versus a Class B address versus a Class C address are going to give us some specific sets or specific values. A Class A address, the entire first octet is used for the network. In a Class B address, the first 2 octets are used for the network. In a Class C, the first 3 are used for the network. Now, it goes a little bit beyond that, because what ends up happening is that Cisco's determined, or not Cisco, the world has determined, that what we're going to do is we're going to fix the values for the first digit, the first most significant bit in the 8-bit field, the second, or the first 2, and then the first 3. And all it's going to do is 0, 1, 0, 1, 1, 0. Now, if we know that this 0 is the 128 range, if it's 0, it's going to equal 0 all the way across the board. If I change this to 1, then the maximum value that I can have is going to be, the idea of 127. So if I added all of these up, that's going to be 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. That's going to add up to 127. So to determine or to see a Class A address, to pick out a Class A address, if I see an address range of 0 to 127, I know it's a Class A address in the first octet. So now the issue is I've got a value of 0 here, which means my starting value is going to be 128 if everything's 0. Now, these are the only values that I can change to 1s, because this one must be a 1, this one must be a 0. So my range is going to be 128 all the way down to 191. Let me double check that. 128 plus 64, yeah, 191. So if this is the 128th place and this is the 64's place, if I take the 8th place, the 4's place, the 2's place, the 8th place, the 16th place, it'd be the 32nd place. I need to write this out. Let me do it this way. Let me go back over to the whiteboard, because I don't want to confuse anyone. New slide. Now remember, I told you that we would write out the places. So let's just do that. We'll do the one board. So it's going to be 128, 64, 32, 16, 8, 4, 2, and 1. Now what we're going to do is that for a Class A address, all they did was they set this value to 0, which means these values could either be 0 or 1. So that means at the lowest value, it could be 0. At the highest value, if I set all of these to 1, that means it would be 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, which would add up to 127. So if I see an address that says 10.1.1.1, I know that it's a Class A address by virtue of the fact of the first octet. Nothing else matters. It falls in the range of 0 to 127, and that's going to equate to a Class A. I also know it's going to have a /8 subnet mask, which tells me these values, all 8 of these have to be the same. So let's take a look at the next one, a Class B address. The Class B address says this one must be 1. In fact, what I'll do is I'll do these in red. Oh. I will do these in red. The ones that aren't allowed to change, I'll do them in red. So 0. So now we have 1, 0. So if these aren't allowed to change, 0 means 64, 1 means 28. So that means the lowest numeric value that I can put in place is going to be 128. So that's my lowest. Now that means the rest of these numbers could be 0 or 1. So again, 1 means that would be the highest value. So if I set all of these fields to 1 down here, what that's going to do is that's going to add up to 128 plus 32 plus 16 plus 8 plus 7 plus 1 plus 2, which is going to add up to 63. So if I come through here, it's going to be 191. So that's going to be my highest value. So if I have a subnet that is 172.16.0.3/16, because remember, Class B has a subnet mask of 8, Class A has a subnet mask of 8, Class B has a subnet mask of 16. What we see here is that I see 172, it's between 128 and 191, and I recognize that immediately as being a Class B address. The last one is going to be the Class C. And what they've done is they've changed it to where it's going to be 110. So now, if I take 128 and add it to 64, since both of these are 1s, then what that's going to do is that's going to give me a starting range of 192. Notice it's 1 higher than 191. And it's going to take me all the way out to where these can either be 0 or 1. Which means from here to here means this is going to add up to 16 plus 8 plus 30 plus 4 plus 2 plus 1 equals 31. I add 31 to 192. And I'm going to get, let's see, 31 to 192. So it's going to be 3. 9, 10, 11, that's going to be 3. So 9, 10, 11. So 213. 9, 10, that can't be right, it's 223. So it'd be 223. My math is wrong. So 3, 9, 10, 11, 12, 223. Yes, that's right. So this is how you would know, or how you would actually know if you forgot to memorize the range. So at the end of the day, our ranges are going to be for a Class A, it's going to be anything from 0 to 127. For a Class B, it's going to be 128 to 191. For a Class C address, it's going to be 192 to 223. And that's going to be simply by looking at the first octet. So if I see 192.168.1.1, I know it's a Class C address simply because the first octet falls in this range. So again, pretty straightforward, pretty simple when it comes to looking at it with regard to implementation. Let me cut back to the presentation. So that's all we're trying to illustrate here. Also, in the confines of this illustration, they're showing us the masks, or the subnet mask. It's not the subnet mask, it's the network mask. So for a Class A, like I said, it's going to be /8, which means the first 8 values can't change. For a Class B, it's going to be 16, which means the first 2 octets can't change. Then it's going to be /24, which means it's going to be 8 plus 8 plus 8 adds up to 24, which means these can't change. So as you can see, if I want to support more hosts, I need or want to use a Class A. Because what ends up happening is that I'm going to have the capacity of supporting multiple users. So here, I can only have 255 total hosts mathematically. Here, up here, let me go ahead. Let me bring up a calculator. Let's just do the math. So, bear with me one moment. So, I remember where they put the calculator on the Mac. There it is. So I dragged a calculator over here. So here's my calculator. So if I have 255, no. So 255 possibilities. So here I have, like I said, 255, and I have 255. So if I take 255 and times 255, what ends up happening is that's going to give me the maximum number of hosts I can support. So 255 times 255, that means I can support, in this scenario, 6,000. So on a Class C address, I can support up to 255 hosts. Mathematically, we're going to learn some variances here. Here I can support 65,025 hosts. And then if I continue my logic where I have 3 octets in a Class C address, that means it would be times 255 again, which means I'm going to have the capability of supporting something like 16 million hosts. So should add up to, a Class A address is going to support 16.5. So let's just say, just to round up, so because I got 8 and then 5, so let's say we're going to be able to support 16.6 million hosts. So that's a pretty big network, pretty big infrastructure, pretty big topology. And looking at that, all this does is going to draw everything from the basic math. So again, what we're going to find is we have this line defining hosts and defining the network. The network mask or the network value gets longer the further we go down. Now that means we need to be very attentive to a number of components that are going to be important for us, and it's going to boil down to this range. So like I said, I did the math, but there's a value or something that I didn't do. Notice I said we had a capability of 255 hosts. Well, mathematically it comes out to 256, but what we're going to do is we're going to subtract 2 of those, and that's going to give us 254. So on each of these scenarios, based on the number of hosts, we're always going to lose 2 addresses. One is going to be the network address, which is going to be the value that is all zeros. And then the other one is going to be what's referred to as the broadcast address, which is going to be all ones. So that's going to be our lowest and our highest value. So our lowest and highest value in a range are going to be lost, because they're already defined. I can't issue them to a host. So when we look at this, like I said, notice mathematically, I said it was 1 to 127. Well, you have to understand 127 is a special reserve value, so we can't assign it to a device either, leaving us 1 to 126, and then 128 to 191, and then 192 to 223. I showed you how that was derived, and we can also see, like I said, 127 is assigned, it's a Class A address reserved for the loopback testing, and we can't assign it to a specific device. So we go anywhere from 254 all the way up to 16 million hosts in our configuration. So again, very handy to know, also really important to know how to actually extrapolate it. Now we have reserved addresses. The reserved address ranges are very significant because they're going to be reserved for special purposes, like that 127 was reserved for loopback addresses for testing. Now when we go in and we start looking at this, what we have to recognize here is that there are reserved IPv4 addresses. Like I mentioned previously, the network address. The network address is going to be where it's all zeros. The directed broadcast address is where all the host bits are ones. Then we have a local broadcast address. We have a local loopback address. That's that 127 we were talking about. And then we have the all zeros address. So keeping in mind the fact that as we go through, not only do we have to understand the idea of Class A, Class B, Class C, and ultimately you're going to have to know Class D when we start talking about multicasting later on in CCNP, but the main thing that you need to grasp here is the fact that we have those 3 categories, and inside of each of those categories, we're going to have ranges of addresses or groups of addresses or individual addresses that are going to be set aside for special purposes, like that 127 in the context of our Class A address range. The other option that we're going to find here is that we need to recognize the fact that IP addresses are not the end-all be-all of existence. For instance, I don't go to my browser and type an address, an IPv4 address, to reach somebody like Google. Let me illustrate something here. I'm going to take myself off camera, and what I'm going to do is I'm going to go back to our presentation, back to the whiteboard. I want to illustrate something. Now, what ends up happening is this. I want to go to a website. I want to go to www.google.com. All right, let me bring up a browser. I've got several open, but I want to have one that's clean. So, need a browser. Got one right here. And all I'm going to do is I'm going to go to google.com, just like I illustrated. So I'm going to come up here and I'm going to type www. I'm on the wrong keyboard. I'm going to type www.google.com and I'm going to hit enter. And it's going to take me to Google. All right. Now let me show you something else. Let me open up a console session. So let me drag this over. Make sure you guys can see everything. Now look here. I'm going to ping. I'm going to say ping www.google.com. Now notice what happened here. Waiting for it to do its thing. I'll go ahead and stop this process. Control C. Oh. Okay. Now look, I typed ping.google.com. Ping www.google.com. And notice it came back with a physical address. So 74.250.125.225.180. I'm going to copy that. I'm going to hit Command and I'm going to hit copy. And then what I'm going to do is I'm going to go back to my browser. And right here in my browser, I'm going to clear this out. And what I'm going to do is I'm going to put that in here. I'm going to hit 74.125.225.180 and I'm going to hit enter. And what you're going to see is it's going to take me to Google. Now, let's do another one. Let's verify. What I'll do is I'll bring back up my session here. Let's ping another site. Some of these don't resolve properly, so let's say ping www.microsoft, let's say Cisco, cisco.com. All right, and I'm going to hit C, Control C, and notice it gave me an IP address. All right, I'm going to copy that one. Then I'm going to go back to my web browser, and what I'm going to do is I'm going to delete this, and I'm going to insert that address and hit enter. And what it's going to do is it's going to tell me URL is invalid. Double check. 23. See, like I said, some of these don't marry up. Let me do this. Some organizations block this information. See, notice here I can't even ping Microsoft.com. See if I can ping another one. Let's see what's another. Verizon.net. Control C. We'll try this one. I don't think it's going to go because notice they're going through an alias. So we'll try it. If this doesn't work, then I'll go back to my Google example because I knew it worked. Yep, still unblock the URL. So what I'm trying to illustrate here is the fact that when I'm trying to communicate, what ends up happening is that I don't know IP addresses, and IP addresses could change. In fact, an IP address can be assigned to an individual machine. We can have clusters of machines. We can have all types of things actually happen in the infrastructure. So what we do is we resort to a technology called DNS, Domain Name Services. Now, DNS is really important because what ends up happening is if I have a host and I'm connecting via this host to the internet at large. So I'll draw a router just because I'm a good boy and we need a router in our infrastructure to get to the internet. I'll draw my cloud. So this is the internet. Now out here on the internet at my service provider is a DNS server. Now I want to get to google.com, www.google.com. Now that's on a server. But the problem is that I don't have the IP address of that server. And we said that IP protocol uses the logical addresses. But I don't know what that address is. But what we do have is we have a DNS server that's normally hosted by our service provider, by our ISP. So what's going to happen here is I'm going to send that message that I want to go to www.google.com. And it's going to go to my router. And my router is going to look at this and say, all right, well, you've got a DNS server configured here pointing to a service provider. So this message is going to get relayed out to the DNS server. The DNS server is going to look at its listing, its A records, and it's going to say, oh, this is www.google.com. Here's its address. And it's going to provide that information back to me. And once I have that information, then I can actually go to the server itself. That's the process that we're going to be discussing and outlining, and DNS is one of the network services that we rely on to be able to provide these capabilities. Let me bring back the presentation, because that's what we're illustrating right here. I'll take my big old head out of the way and let's walk through it. So if we look at the scenario like I described, here's the DNS server. We have different DNS servers. We have also the server that I want to work or reach. This is all taking place on the internet. So here's the situation. 1, my computer sends a message. I need to access cisco.com. What's its IP address? That message gets sent up the line to my DNS server. The DNS server says the domain name cisco.com is not in my database. So what it has the capability of doing is it has the capability of sending it to another DNS server. Ideally, this one may be an internal DNS server that I run. This one may be the service provider's DNS server that knows everything. And then ultimately what's going to happen is that response is going to get relayed back to this one, this DNS server, and then the information is going to be sent to us such that now we have the IP address 198.133.219.25, and now it's going to be able to send our packets directly to this destination. And this is the exact process that takes place every time we try to browse or ping based on a URL, based on the actual website human readable name. Now when we look at this, it's going to be this process that allows us to communicate to the outside world, and DNS servers are extremely important because what they do is they provide the information needed to be able to access the outside world. And that information has to be stored on our machine. Behind me, what we see is an example of an output screen on a Windows computer that's showing the output of something referred to as the ipconfig command. Now we've executed ipconfig /all because we want to see everything. And what we're going to notice right here, and I'm going to grab a white pen so I can write on this black console. Notice it gives me my host name. It gives me the information associated with my DNS servers. So these are the IP addresses of the servers that I'm going to use to resolve human readable names to actual IP addresses so that I can send information to my devices and actually get forwarded the way that I want everything to go. It's also going to give me my network. It's going to give me my subnet mask or my network mask. And most importantly, the key element here is going to be this idea of a default gateway. So if I don't know the identity of a destination, the default gateway is where I'm telling my system to send it so he can find out. And again, it all is part and parcel of ensuring that our infrastructure is fully operational and integrated to communicate to other components like domain name servers. Now, if I want to look at the statuses of these, so for instance, we've talked about addresses, and we said that addresses, logical addresses, IPv4 addresses in this instance, can be assigned to individual ports. How do I know what address has been assigned to my devices? Well, the output that we see here is the result of a show. Let me grab a color pen here, is the show IP interface brief command. The show IP interface brief command is going to give me a list of all of my addresses. Notice here VLAN 1 has an IP addresses. The others are all unassigned, so we haven't given anything, and we can also see that we're up on the link that we have configured. So again, the output of the show IP interface brief command is very useful. We could also filter it. I could come in here and say show IP interface brief pipe and say exc for exclude and say assigned the first part of this, and what will end up happening is unless there's an address here, it's not going to show up in the output. I'll illustrate that when we actually bring up the equipment, because that's possibly one of my favorite things to do when it comes to interfacing with my gear. Now, we've outlined the fact that all of these components, all of these piece parts work together so that we can communicate with the outside world. There's more to it than this. We've talked about what happens with the IP addressing, and we need to have more experience with that. So I'm going to try to come up with some worksheets and some workbooks that we can do in order to be able to go through some subnetting components. But right now, the key thing for me and you is for you to understand the fact that our addressing is hierarchical by design. Our address is broken up into multiple classes, Class A, Class B, Class C. Understand how to actually derive those values, memorize the listing, and be cognizant of the fact that the first octet defines what access or what class of address it is that we're looking at. We looked at how to display what information was running on a given interface. We looked at what's going on with regard to doing the assignment and other previous configurations and walkthroughs. So right now what we want to do is we want to leave this lesson with those key elements in place and go into the next lesson and be mindful of exactly what's happening when we start extending IP access to the internet to our users. I'll see you guys in the next presentation. I hope this was helpful. Bye-bye.